These are the review exercises from Chapter 5, and in this set we're going to look at a variety of integration problems. So it's going to be important to analyze the problem and determine the best strategy to proceed. So let's jump right in with problem number 5. In problem 5, the integrand is a fraction with a monomial denominator, one term in the denominator. So this is a break apart, or as we like to say in class, Miss Oliver math. So x cubed over x squared is simply x when we reduce that. And 1 over x squared can be rewritten algebraically as x to the negative 2 power. And so when I find the antiderivative, I get x squared over 2. And for x to the negative 2, I'm going to increase the power by 1 and divide by that new power. And you might find the answer written as 1 over x, depending on if it were multiple choice or a show your work question. Make sure you do not forget the plus c. Problem number 6. Same situation, we can reduce each term in the numerator by x squared. So my rewrite in number 6 will be x to the first power minus 2, because the x squares divide out, plus x to the negative 2 power dx. So this is after algebraic manipulation or fraction manipulation. It's a normal problem, quote unquote. So we get x squared over 2 minus 2x minus x to the negative 1 power. Don't forget plus c. Moving on to number 8, it is another quote-unquote normal problem. We have to know our trig derivatives / antiderivatives. So we ask ourselves, what function has a derivative of cosine? The derivative of sine is cosine, so the antiderivative of cosine is sine x. Then we play the game again, and we ask ourselves, what function has a derivative of secant squared? The derivative of tangent is secant squared, so when we anti-differentiate, we get 2 tangent x plus c. Don't forget the c. Problem number 10. Oops, edit undo. I meant to reset, not clear the annotations. Problem number 10. Another normal problem. It requires no manipulation of any kind. The antiderivative of t is t squared over 2. The antiderivative of e to the t, which is our favorite function of all, because the antiderivative is e to the t. Don't forget the c. All right, let's see what our next problem is. So now we go to problem number 44, which now we have a definite integral. And we are evaluating that, secant squared. We just played with that just a few moments ago. So when I find the antiderivative of secant squared, I get tangent t, and that's going to be evaluated from negative pi over 4, whoops, that's a negative, to pi over 4. And by the FTC part 1, I'm going to evaluate at the upper bound, minus evaluate at the lower bound. And now I have to stop and think about my pre-cal and my trig values. Fortunately, they gave me pi over 4 because the sine and the cosine, as you recall, of pi over 4 is root 2 over 2. Pi over 4 for the first term is in quadrant 1, and in quadrant 1, both the cosine and sine are positive. So if we put that number over itself, we will get 1. And then looking at the lower bound, negative pi over 4, recall, is rotated in the opposite direction. So we are now in the 4th quadrant. And in the 4th quadrant, cosines are positive and sines are negative. So we're going to get a negative 1. So that's minus negative 1, which is 2. So that is the net accumulated area from negative pi over 4 to pi over 4 for tangent t. Our next problem is number 61. In number 61, let me get myself a little bit more paper here. In number 61, they want us to find the derivative of a definite integral. So remember, when we're finding the derivative of a definite integral, the first thing that we want to look at with our math eyes is, do we have a constant low bound? And we do, so we're good on that. The new function in this case is a simple one. The new function is just x. So the steps, remember, f prime of x is we take out the dummy variable of t, so there's the t taken out. That was t squared, now it's blank. I'm going to take out the t of the second term, so 3 parentheses, and I'm going to have the plus 2. As we said, the new function is x, so after I take out the dummy variable, or the t, I put in the new function. And then lastly, I'm going to multiply by the derivative of the new function. The new function is x. So I'm going to take this expression and multiply it by the derivative of x, which in this case happens to be 1. So the derivative of big F is simply x squared plus 3x plus 2. In problem 64, we are finding the indefinite integral, so I'm going to need to remember my plus c's again. So I'm analyzing and evaluating what I want to do with number 64. I could make a common denominator on the inside, but the first thing I'm noticing is the square. So to find the antiderivative, I'm going to do the algebra, and I think when I do that, I'm going to write that as go ahead and write it as x to the negative 1 power. So when I square, my integral, just a rewrite here, is going to be x squared minus 2. Now, when you multiply x times x to the negative 1 power, that might be better in that case to go back and look at it as 1 over x, because it's a whole lot easier to see that the x's divide out. So I just get a 2 when I get my next term, and then I'm going to square the last term, and so I get x to the negative 2 power. Now you can FOIL that out the long way or whatever works better for you. Now that makes it into a what we would call quote normal antiderivative. So I have x cubed over 3 minus 2x minus x to the negative 1. We've seen that a lot in this set. And so that's my antiderivative, nothing fancy, no u sub, just a normal problem after some simple manipulation. All right, number 66. In number 66, I clearly see an inside function right here. And so I'm going to go to u substitution and see what happens. So u is equal to x cubed plus 3. du is 3x squared dx. I don't need that 3, so I'm going to divide it to the other side. I'm going to rewrite my new integral. There's my 1/3 coefficient out front. In place of the x squared times the dx, I'm going to substitute the du, so that's going to go in the back. In place of x cubed plus 3, I'm going to substitute u. That's to the 1/2 power. I'm going to increase the power by 1, so that's going to give me u to the 3/2. Divided by 3/2 is times 2/3. Don't really have to have the plus c there. So now I'm going to replace the x cubed plus 3, so that's 2 x cubed plus 3 to the 3/2 power over 3 plus c. Don't forget the what? C. 68. In number 68, I see a rational function. I see that my denominator is being squared. I'm certainly not going, I'm looking right here, I'm certainly not going to square that trinomial unless I absolutely have to. So my reaction, I think I'm going to go with u sub, and I'm going to let u equal to the inside function, not the entire denominator, but the inside function of x squared plus 6x minus 5. The derivative of that is 2x plus 6. And if I factor out a 2, I will get the x plus 3. There's my dx. My x plus 3 in the numerator. I can divide the 2 to the other side. And now I think I have everything I need. So I'm going to have a 1/2 coefficient out front. I've got my numerator replacement. I've got my, oh, that's a dx. I got my dx replacement, and so that ends up being 1 over u squared, which is the same thing as 1/2 integral of u to the negative 2. They really like that one. We've hit that a lot. So I'm going to increase the power by 1 and divide by the power. So that's going to give me, I'm trying to decide how I want to write it. Since the 2's already in the denominator, I think I'm just going to move. In this case, I'm going to take the u down to the denominator and make that power positive. I'm going to make my final replacement. So u is equal to x squared plus 6x minus 5. I can distribute the 2. I cannot distribute the 2. It doesn't make it better or worse by distributing. And don't forget the c. All right, that was number 66. Moving on. No, that was 68. Moving on to number 70. Number 70, with my math eyes, I see trig, and I see multiplied by x. And my math eyes, even though there are no parentheses here, I know that parentheses go around that angle. I'm thinking u substitution, so u is equal to 3x squared. Du is equal to 6x dx. Don't need the 6, take it to the other side by division. And I have what I need. So I'm going to rewrite my integral to be 1/6 of sine u du. Tricky trig, be careful. Tricky trig, be careful. What function has a derivative of sine? Well, we know that the derivative of cosine is negative sine. So we're going to have to reintroduce the negative. Cosine of u plus c. So negative 1/6. Cosine, replace 3x squared plus c. Don't forget the c. 74. In number 74, I see a familiar trig derivative or however you want to think about it. When I say that, I'm basically saying I know a function that has a derivative of secant of the angle, tangent of the angle, and that would be secant. But I do have something going on with my angle here, so I'm going to do a u sub, and I'm going to let u equal to the angle of 2x. Du is equal to 2 dx. Divide the 2 out because I do not need it. My new integral becomes secant u tangent u du, and as I said, the antiderivative of secant u tangent u is secant u. There's my plus c, 1/2, replace, and voila. Guess what? Don't forget the c. Let's go on to number 84. All right, in number 84, we are evaluating with definite integrals, and we're going to use, after we do it by hand, we're going to use a graphing utility to verify your results. So really, this is just an opportunity for you to practice using your calculator to make sure that you can get the answer that you actually are supposed to get. So in number 84, I think the first thing that I want to do here is to get that coefficient in the denominator of 3 up front to make that a 1/3. Integral from 3 to 6 of x over square root of x squared minus 8. I see an inside function of x squared minus 8, so I think I'm going to go with a u sub. So the x squared minus 8, the derivative of that would be 2x dx. I don't need that 2, not in the problem. So now this 1/2 right here is going to go as a coefficient with the 1/3 that's already out there. So I have 1/2, I'm going to do that in blue so you know where it's coming from, times the 1/3 that's already there. New integral is going to be 1 over u to the 1/2 power du, which is 1/6 of the integral u to the negative 1/2 power du. I'm going to increase that power by 1 and divide by that new power, plus c it, and then I'm going to replace. So let's see, 2 divides into 6 3 times, so that would be 1/3. My u is x squared minus 8 to the 1/2 power. You could, of course, write that as a square root if you wanted to, and that might be how an answer appeared in a multiple choice set. All right, so I've actually forgot that this is a definite integral, so let me back up a little bit here. Get my eraser cranking here. Yeah, it's actually working. So I'm going to get rid of this, and I'm going to come back and I'm going to neaten things up a little bit. So let's go back and look at the bounds. And remember, we are going to change the x bounds right here. This is an x value. and we're going to make it into a u-bound. So I'm going to substitute it here. So 3 squared is 9, and 9 minus 8 is 1. So my new bound, or my u-bound, is 1. A 6 goes here. 6 squared is 36. 36 minus 8 is 28. So that's going to be my upper bound. All right, I'm going to redo the anti-differentiation. So there's my 1, 6, and I'm anti-differentiating. Come on, Jernigan, you can do it. So anti-differentiate is going to give me u to the 1/2 power, or so 2u to the 1/2 power from 1 to 28. I'm going to go ahead and simplify the 2 and the 6 and get that out of my way and make it 1/3 of u to the 1/2, which is square root, from 1 to 28. Substitute, and that will give me the square root of 28, upper bound, minus the square root of 1, which is just 1. And when you use your calculator to check this, then you're going to have to change this number right here into a decimal value to compare it with your calculator. Problem number 88. Let's bring this down, or 86, I'm sorry. Let's bring this down. So problem number 86, I see an inside function. So I'm going to let u equal to x plus 1. du is equal to dx. So I can replace the x plus 1. I can replace the dx. I'm not bothered by the 2 pi, but I am a little bothered by this x squared right here. Uh-oh. Seems like that x doesn't want to go away. It's being pretty, what? Stubborn. Yeah. So I'm going to come back to the statement where u is equal to x plus 1, and I'm going to figure out what x is in terms of u. So if I evaluate that, I'll get x equal to u minus 1. So now I have a replacement for that x right there. Now be careful. I'm going to keep the 2 pi out front. I'll change my bounds in just a second. In place of the x, I'm substituting u minus 1. So it's a u minus 1 squared. And in place of the x plus 1, I'm going to have u to the 1/2 power. Let me go ahead and change my bounds so I don't forget that we're doing a definite integral. So now I'm going to substitute -1. And since I have it very clearly written out here, I'm going to substitute, actually, no, I'm not. I'm going to substitute it here. So -1 plus 1 is 0. The upper bound of 0, 0 plus 1 is 1. So the bounds are in the right order. I don't need to do anything there. Moving forward, I'm going to square the binomial. I'm not integrating yet because I still got some cleanup to do. So u squared minus 2u plus 1. Still not done. I got to do some more cleaning, some more algebraic simplification. So that's 2 pi. Not integrating yet. I'm going to distribute the u to the 1/2 to each term. So that's going to be u to the 3/2. Take your time when you're doing that. Minus 2u to the u to the 1/2. Let's get rid of, hopefully you'll know, I better get rid of the stray mark. Eraser, come back. There we go. There we go. And of course it was too big and I erased the other stuff. So 2u to the 1/2. No, that's not right either. Let's try this again. I am subtracting my powers. All right. That never happened. 2 pi, 0 to 1. So 4/2 and 1/2 is 5/2. I was dividing, not multiplying. My bad. 2u to the 3/2 plus u to the 1/2 power. So hopefully you got it right and you were ready to tell me I messed up, but then I fixed it. Yay. All right, now I'm going to find the antiderivative. So there's the 2 pi. And that'll be u to the 7/2 multiplied by 2/7 minus u to the 5/2 multiplied carefully by 2/5. So that'll be 4/5 plus u to the 3/2 multiplied by 2/3. thirds, evaluated, thank goodness for that 0. 0 to 1. All right, so now I'm going to substitute. So I still have my 2 pi. And 1, the number 1 raised to any power is 1. So I simply get 2/7 minus 4/5 plus 2/3 minus 0, because if I substitute 0 in all three terms, I will get 0. All right, then I'm going to do a common denominator of 7, 5, and 3. And that common denominator is a 105. So the common denominator is 105. All right, so 105 divided by 7. Whoops, 105 divided by 7 is 15, and 15 times 2 is 30. 105 divided by 5 is 21, and 21 times 4 is 84. And 105 divided by 3 is 35, and 35 times 2 is 70. And then combine the numerator, 30 minus 84 plus 70 gives me a total of 16. So 2 pi times 16 over 105. And you can make that into 32 pi over 5. Let's see what our next problem is. That was number 86. So now we're going to the next set of 97. So let's do a reset here. And slide this down and make myself some more paper here. All right, problem 97. We're back to indefinite integrals. So what do we got to remember? Plus C. Problem 97, I have a denominator of 7x minus 2. I have a rational function. So I am thinking in 97 of letting u equal to the denominator, 7x minus 2. The derivative is 7 dx, and I don't need the 7. So I'll get that out of the way. My rewritten integral would be then 1/7 of 1 over u du. So that's going to give me ln, absolute value of u, plus c. Do my replacement, and I get 1/7 ln, absolute value of 7x minus 2, plus c. Number 99, I have another rational function, where I have a function that has a fractional function. So I'm going to let u equal to the denominator of 1 plus cosine x. Du, the derivative of 1 is 0. The derivative of cosine, be careful, tricky trig, is negative sine dx. I don't need that negative, so I'm going to get it out of the way. I'm going to do my rewrite of minus 1 over u, and we're back to ln, so minus ln, absolute value of u plus c, make the replacement, negative ln, absolute value of 1 plus cosine x, and plus c. And then finally, number 101 is back to a definite integral. So in 101, I got to remember to change my, Miss Oliver math, look at it, it's back. So I'm going to do a rewrite on that one to be from 1 to 4. I'm not even going to have to change the bounds. So that will be 1 plus 1 over x, or x to the negative 1. Now, notice this time I didn't bring the variable up with a negative power, because I want my math eyes to see 1 over x, because the antiderivative is ln. So the derivative of 1 is x, the derivative of 1 over x is ln, absolute value of x, evaluated from 1 to 4. So upper bound 4 minus ln of 4. I don't need the absolute value, because the absolute value of 4 is 4. 1 minus ln of 1, and the ln of 1 is 0. You have to know that. So then I have, careful, I have 4 minus 1 is 3, and then minus ln of 4. That would be the net accumulated area under that curve from 1 to 4. And that's it for this set, so hope it helps you.